Good afternoon. It's great to see you all here. So I'll be talking about moisture and using cavities in constructions to manage moisture, so specifically about the M in HAM. So my topic is know your cavity. So construction cavities have purposes for both managing the amount of wetting that occurs in construction systems and the amount of drying that can be achieved within construction systems. So traditionally we've used cavities and insulation about the dew point to manage condensation in construction systems. So we look at the temperature profiles across the construction on assumptions on temperature inside and outside of the building, and basically look at the surface conditions and whether dew point is likely to be reached and condensation might form on the internal linings or external cladding. And in terms of using membranes in buildings, we've always followed the rule of thumb, which is put the vapour barrier on the warm side of the construction system. But this has issues. There's problems with this because it's not always easy to tell which is the warm side of a construction system. So in climate zones 4, 6, 7 and 8 of the BCA, the cooler climate zones, the warm side's not necessarily the outside of the stud-work. It could be on the inside of the stud-work. So this is the warm interior conditions in a cool climate. And therefore we're putting the vapour barrier on the wrong side of the stud-work. So I'll go into more detail in this, about this later. So recently there's been an increased national focus on condensation and moisture control in buildings. Last year the ABCB released the second edition of the Condensation Handbook. Last year again, the Tasmanian government put out the Tasmanian Building Designers Guide, which was all about condensation in buildings. And this year, the NCC released new verification methods for facade systems or wall systems. This is all about reducing the amount of wetting or waterproofing of walling systems. So in August 2014, the Premier of Tasmania put out a press release saying they've launched an investigation to Tasmanian leaky buildings syndrome. So this is very similar to what happened in Tasmania 10 to 15 years ago, where constructions got wet, liquid water ingress and condensation forming in constructions. They weren't able to dry out, the buildings rotted, huge amounts of structural damage. So in the BCA we have specific clauses in the health and amenity section, and it's all about managing damp and waterproofing of buildings. And the objective of this part is to safeguard occupants from illness or injury and protect the building from damage caused by, and then it talks about surface water, which is external water basically, external to the building. So we're talking about rain and deflecting and draining that rain, and external moisture entering the building. So that could also be not just liquid rain, but it could be external humidity. So that's more of a tropical climate issue where you have large amounts of moisture in the air outside. More for cooler climates is the accumulation of internal moisture in a building. This can be the largest problem for cooler climates, where we have indoor activities such as cooking, washing, breathing, all expelling moisture into the indoor air. This is where it links into the air tightness and what Angus was talking about, and the accumulation of the moisture in a more airtight building can be more severe. So we have to manage that internal moisture. So the question is, have we got our designs right to meet these objectives in the BCA? What you're seeing here is a Tasmanian roof, and it's pretty obvious here what's happened is the amount of wetting in this construction system has far outweighed the amount of drying or the drying capacity of this system. So timber's become wet, stayed wet, and mould started to grow on the battens and the roof trusses. In this case, what you're looking at is a roof in New South Wales where condensation's formed under the sarking on a tiled roof. And what you can see is the condensation running down the bottom of the foil vapour barrier sarking. So when you think back to Scott's presentation about the perimeter bats, the issue we have here is if the perimeter bat or the insulation is touching the sarking at the perimeters, then you've got that potential for tracking of that condensation straight onto insulation, onto the ceiling linings, and potential damage. So we don't necessarily know there's a condensation problem until we might see it occur on the internal linings. And this could be mould growth, it could be ghost leaks, which are those leaks that appear on the roof but they're not actually roof leaks, it's condensation dripping, or it could be structural damage or physical damage of the internal linings themselves. In this wall system, the method in which this wall got wet is not 100% clear. It may have been liquid water ingress or it could have been condensation. Either way, the drying capacity of the wall system, the method in which it was drying wasn't there to allow that moisture to dry out, and therefore what you're seeing is the corrosion of the metal bracing and discoloration of the insulation. So every state in Australia has guidance on how to clean up mould in buildings, but there's no specific guidance on how to design buildings to prevent mould. In New Zealand, they made an expensive mistake. The leaky buildings crisis they had 15 to 20 years ago, $11.3 billion worth of damage. This was a figure from 2009. It's probably closer to $20 billion now. And from this mistake, they came up with a new design philosophy. It was called the 4Ds theory, and it's about deflection, drainage, drying, and durability. So deflection and drainage is all about using cladding materials, sarkings, to deflect and drain liquid water or rain, and building in drying capacity, so the drying mechanisms, whether that be ventilation or using breathable, vapor-permeable products, and selecting materials that are durable and can actually withstand the amount of moisture which they'll be subject to. So in order to design buildings that are robust from a moisture perspective, we need to understand how moisture actually transports throughout the building envelope and through the construction systems. And there's three main mechanisms or three main ways which moisture moves. There's capillary action, which is liquid water transfer through porous building materials. There's air transported moisture, which is when you have basically humidity or water vapour in the air, and anywhere the air goes, the water vapour will go with it. Then there's vapour diffusion. So when you have a temperature and humidity differential on either side of a construction system, if you have porous or vapour permeable building materials within that construction, the water vapour will actually migrate through the materials themselves. So as a matter of getting moisture design right, as a priority, we have to look at getting the liquid water management correct. And to do this, we need to look at doing things like face draining window sills rather than using sill drained windows that will dump moisture behind the cladding. If the moisture is dumped or the liquid water is dumped behind the cladding, then the construction system, the wall system, is going to have to deal with that amount of moisture and dry it all out so that it will not rot or produce mould. So all construction materials have different degrees of vapour permeance or vapour permeability. So mineral fibre insulation and plasterboard are two of the most vapour permeable products that you can buy. As opposed to on the other end of the spectrum, we have materials such as metals and glass, which are basically pure vapour barriers, and no water vapour will transport through those construction materials. Foil face membranes are also vapour barriers, and we need to note that insulation boards are generally nowhere near as vapour permeable as mineral wool insulation. Last year, CSR did some investigations into the drying rate or drying capacity of construction membranes. And as a golden rule, the golden rule is never completely enclose construction systems in vapour impermeable materials, because basically we found that's a good way to make mould grow and timber rot. And we found during this experimentation that vapour permeable membranes will dry 75 times faster than vapour barriers. So these are the foil face membranes, and they will dry 7 times faster than the perforated foil barriers. So there's three main types of construction membranes on the market these days. There's vapour barriers, so basically the traditional foil face membranes. There's perforated foil membranes, and there's new generation material engineered products. So the vapour barriers, basically they won't allow any water vapour to transport across them. Because of that layer of aluminium, they are basically almost 100% vapour barriers. They are also air barriers, so they will help us achieve the air tightness goals or the air infiltration that Angus was talking about. And they have this low emissivity aluminium foil surface that when you face this into a construction cavity or adjacent an air gap, it will help improve the thermal performance of the construction system. The perforated vapour barriers, They are vapor permeable because what they're doing now is they're allowing air to transport through the holes, and they're achieving that vapor permeance through air transported water vapor. So they're no longer an air barrier because you've obviously punched holes all through it, so it's not going to be nearly as effective in achieving air tightness requirements and energy efficiency, but it does still have that lower emissivity aluminium foil surface that will give you an enhanced R value when you face it to a construction cavity. And the new generation material engineered products, which are vapor permeable products. So they're also engineered to be air barriers. However, they don't have a foil surface, so they're not going to help you achieve or increase the R value using air gaps and those reflective surfaces. So when we talk about the word breathable, it's a word that's thrown around in the industry quite often, and I've spoken to architects, engineers, building scientists, energy raters, asked them what is breathable, and every time you get a different definition and a different answer. And that's because both the new generation products are marketed as breathable, as well as the older generation perforated wraps. So both of these are vapor permeable, but the key difference here is that the new generation ones are air barriers, and the perforated ones obviously not air barriers. So a good quality breathable wrap or a good quality vapor permeable wrap will be vapor permeable, and it will be an air barrier. So when we talk about air barriers, there's two fundamental types. There's the old traditional foil face membranes, and then there's the new generation engineered products. So both of these products are water barriers, so they're useful as sarkings, and both these products are air barriers, but one is vapor permeable and one will now allow no water vapor to transport across it. So when we want to understand how to use these different types of membranes, there's some calculation methodologies out there that will help us do this. There's a static state calculation outlined in ISO 13788. So what this means is it uses average monthly indoor temperature and humidity and outdoor temperature and humidity, and from this you can calculate a temperature profile across the wall and a dew point profile, and from this it will give an indication whether condensation is likely to form and the risk of damage to the construction system. So CSR has actually utilised this calculation methodology on this wall system, for example, which is a lightweight CLAD direct fix fibre cement system. It's got an R2.5 wall bat in there, which is 90 mils, filling the whole cavity. And then what we did is we varied the type of wall wrap in there using the calculation methodology. And what we found is with a vapor barrier, the traditional foil wraps, there's a high risk of condensation forming in many parts of Australia. If we then go to a perforated foil wrap, the risk reduces, but still in Victoria there's condensation risks in basically all of Victoria. We then go to the new generation vapor permeable wraps, and what you see is that it's almost eliminated the risk of condensation in all coastal regions, and it's only the mountainous regions where there might be a risk of condensation. If we then enhance the system a bit further and say, well, let's build the cladding off the stud work by 20 millimetre battens, then the risk almost eliminates itself throughout Australia, except for the snowfields you can see dotted on that map there. So there is an issue with this ISO calculation methodology. It only considers vapour diffusion, so it's only looking at the temperature and humidity on each side of the construction system. It doesn't take into account liquid water, so it doesn't take into account the rain load on the wall. It doesn't take into account the wind-driven rain and the wind pressures. It doesn't look at sunshine and the drying capacity that the sun might have on that construction system. And it doesn't allow you to say, well, what if the facade should actually leak and I should get some rain or water dumped into that, into the stud bays or into the cavity. So what CSR is using now is WÄRME und FEUCHTE INSTATIONÄR, which is a German software package developed by the Fraunhofer Institute in Germany, which is the leading scientific research organisation in Germany. And it's what's known as a dynamic simulation software package, in which it does similar to what the ISO calculation does, but it will take the weather files or the weather conditions from the location which you design in, and it will do an hourly analysis over a year or several years, and it will look at the moisture flows, capillary action, vapour diffusion, and the drying potential and the wet-in cycles of those construction systems to see if it will be durable over time. So what you might get out of this software or simulation package is something that looks like this. And this is a poorly designed construction system, and I can tell this because I can see the moisture content increasing over the first 4 to 5 years, and it gets to a level that's completely unsustainable, that's going to produce mould and timber rot, and the system's likely to have a very short lifespan. If we then say, well, how do we design that system better by modifying the material layers, vapour permeability of the layers, then a good system, what you will see is drying in the first few months and stabilisation of the moisture content over the seasonal variations, which will stay below a critical moisture content, and therefore it's not likely to produce mould or timber growth, timber rot. So the NCC's introduced new verification methods for the facade systems, and what this is all about is reducing the amount of wetting or the waterproofing of wall systems. And there's two fundamental methods of achieving this. There's the face-sealed approach, and there's the drained and ventilated cavity system approach. So the face-sealed approach is all about using the external render coat or external layer on the outside of the cladding to maintain a waterproof and airtight barrier. And it requires that all windows and doors be well sealed around those openings. Then if we go to the drained and ventilated approach, I'm going to speak a bit more about this because this relies heavily on cavities to achieve its waterproofing. And it's known or commonly referred to as a pressure equalised cavity system. So in Australia, we basically, in detached housing, we build a lot of brick veneer. And the reason for this is brick veneer is basically a drained and ventilated pressure equalised cavity system, and it's tried and tested. It's been around for many, many years. Builders pretty much know that it's going to be relatively safe from a moisture perspective. Architects know that it's going to be safe, so we stick with it. In the multi-unit segment, there's a strong portion of the market which is precast concrete panels. So these concrete panels can either be directly rendered, which would then be a face-sealed system, or you could batten off those concrete panels and put a cladding system over the top and turn it into a drained and ventilated cavity system. In both segments of the market, there's a growing portion of lightweight clad systems. In all cases, in lightweight clad systems, CSR recommends to use drained and ventilated cavity systems to manage the waterproofing and wetting of those wall systems. So, as I said, the NCC, the new requirements, are all about reducing the amount of wetting in walls. So it's about using cavities in the pressure equalised cavity systems. It's all about using those cavities as a capillary break. So any moisture that should migrate through the cladding systems through capillary action, once it gets to the cavity, will drain downwards to the bottom of the cavity and safely drain out to outside. The pressure equalisation relies on there being an air barrier somewhere in that system. And in particular, we need to rely on the vapour barriers or the new vapour permeable wraps as being air barriers as well to get pressure equalisation in these cavity systems. So what you're looking at here is a Cementel fibre cement weatherboard system under test at CSRO in Sydney. And you can see through the window in the back of the test rig there, you can see water dribbling down the back of the weatherboards. So this isn't actually a failure of the system, this is actually what's meant to happen in these systems. So to have a look at what actually happens when you have a drained and ventilated system, if you have wind and rain pressure on the outside of that facade, what it means is because we have an opening at the bottom of the cladding, opening at the top of the cladding, and potentially in all the overlaps of the weatherboards, when you've got that wind pressure on the outside, the pressure will equalise behind. You'll get the same pressure behind the cladding as in front of the cladding. And what that means is you won't get spraying of water across the cladding if you've got a large temperature differential. And the water will just dribble down the front side of the cladding. If it does get through, it will dribble down the back side of the cladding and safely drain away. This system does rely on the membrane, the insulation, the plasterboard, all working together to create as close as possible to a perfect air barrier. And that's why I'm saying air barrier membranes for a drained and ventilated system are important, and properly taping and sealing. So CSR has looked at some rules of thumb from the Building Science Corporation in the US, and basically looked at weather conditions and said, well, where it rains a lot, we need to seriously think about how we design and construct our walling systems. So in the tropical rainforest areas of Cape York, we need to think about how we design those cavities, as well as the west coast of Tasmania. And we seriously need to look at draining those cavities, ventilating those cavities, and then selecting the right materials that are going to be durable to withstand large amounts of moisture. The other function of cavities, obviously, is for drying. So air exchange in the cavities will help us promote drying in our construction systems, and that air exchange can either be accidental leakage within the cavity, or it can be purpose-built ventilation. And we also have the aid of the new generation vapor permeable wraps, which allow moisture to escape from construction systems. So if we take a look at history and say, well, why wasn't there a problem? Back in the early 1900s, we had wall systems, construction systems that had huge amounts of airflow through the cavities. So in this case, a brick veneer wall had the brick cavity which had air flowing up it, and air was free to flow through all the stud bays as well. And that airflow would take all the moisture with it and dry the wall system out. In the mid-1900s, we then added SARKIng membranes to the wall systems, basically typically had a foil layer on them, and this was there for two reasons: as a sarking to stop liquid water transferring into the stud bays or onto the timber frame, and the foil layer was meant to enhance the thermal performance of the wall system. So we got a slight kick in the thermal performance. In 2005, energy efficiency regulations came out, and we started adding insulation, widespread or generally put insulation in our wall systems. And what this does is it means that when the insulation is put in, we trap heat inside the building. So if the inside of the building is going to stay warmer, which we're trying to do, then it stands to reason that the outside of the insulation, or where the membranes sit in, will become colder. So if that membrane is becoming colder, there's a potential increase for condensation risk. Now we have insulation levels which are basically fully filling our stud bays up to 90 mils, 2.5 or 2.7 wall bats. And we've got a larger temperature differential now because we've got more insulation, but we have a choice of membranes. We have vapor control membranes, which includes both vapor barriers and vapor permeable membranes to be able to manage the moisture in those construction systems. So if we look at hot climates and we say, well, how do they design or build construction systems in hot climates? And the traditional method of using a foil-faced vapor barrier is fine on the outside of the stud work. That's on the warm side. That stops the high humidity air from outside migrating to the inside of the construction system, and that's how we want to do it, and it's a very that's the right way of doing it in that climate. If we then go to cold climates and we say, well, what's happening in cold climates? You generally got higher humidity and higher temperatures on the inside of the building. It's going to be lower temperatures and lower humidity on the outside of the building, which is going to want to drive water vapor through those construction materials to the outside of the construction. And what that means is if we use a series of vapor permeable material layers, so vapor permeable plasterboard, vapor permeable mineral wool insulation, and a vapor permeable wrap, that humidity from inside the house can migrate through that wall system to the cavity, and the ventilated cavity will ventilate that humidity to outside, and that construction system will remain free of damage. So when we look at our wall cavities and we say, how do we actually design the detail of them at the top of the wall system, the general or the typical detail will look something like this, which is the cavity will open up straight into the roof space. So what we've got is the cavity, which is designed to expel moisture, is taking all that moisture-laden air straight into the roof space, increasing the moisture load in the roof space, and now we have to deal with that moisture within the roof space. If we then say, well, how's a better way of doing this, and we close off those two cavities, we isolate the wall cavity from the roof cavity, and we put specific built ventilation openings that will ventilate the wall air back out to outside, then we're not adding that moisture to the roof space, and it's a far better solution. Same thing for fibre cement or lightweight clad systems. We've got that ventilated cavity. In this case, if we've got the bead-in along the top of the wall, there still is a small gap between that bead-in, will allow some ventilation of that cavity. If we wanted to improve the drying rate of that wall system, we can specifically build in the ventilation opening along the top of that system, and we'll increase the drying rate and the durability of that wall system. And we've stopped that moisture from entering the roof space. So when we talk about roof space, there's complex interaction between heat, air and moisture in roof spaces. It's similar to the way walls work, except it's slightly different in that it's more about using sarking for drainage, and it's about managing wind loads on the roof and using or utilising air exchange in the roof potentially for drying. So we need to understand air exchange in roof spaces in Australia to be able to design better from a moisture perspective, because air exchange in the roof can both add to wetting of the roof structure as well as drying of the roof structure. So it's very important to understand how much ventilation and where the ventilation is coming from. We need to understand why condensation actually forms in roofs. Back in 2001, CSRO made a statement, and they said high levels of ceiling insulation mean that roof spaces are colder as they are not heated to the same extent from below. So as we increase our energy efficiency regulations, we increase the ceiling insulation level, then that insulation is actually doing a very good job of trapping heat inside our building. That's what we want it to do, but what it means is that the cladding on the outside of the building, the roof cladding, is going to become colder. So the BCA talks a lot about solar reflectance of roof claddings, and you're allowed to adjust your insulation levels based on solar reflectance, light, medium, dark coloured roofs. But on the flip side of that, that's looking at the daytime heat gains. But on the flip side of that, we have nighttime, and we have an effect at night that is all driven by a surface property of our roofing materials called the emissivity. And the emissivity determines how much heat will be radiated by that roof back to space at night. And this is some data from the CSR house roof in Sydney. And what we're looking at is the roof tile temperature is the blue line. And it's from June, July, August last year. So the blue line, you can see the daily variations in temperature swinging by about 50 degrees, getting as hot in the daytime at about 60 degrees, and at night time dropping below zero on occasions. The red line is the ambient external temperature, the air temperature outside the house. And we measured the maximum difference between that air temperature and the roof tile temperature to be 7.6 degrees Celsius. So the roof tiles were actually 7.6 degrees cooler than the outside air temperature. And the roof tiles drop below zero on occasions, meaning that conditions are conducive to condensation forming. Then if we say, well, let's look at the sarking underneath those roof tiles. So we have foil sarking under those roof tiles. In this case, the foil is doing pretty much the same thing. The blue line, it's got large variations in temperature swing between nighttime and daytime. But the sarking, when you look at the difference between the temperature, the air temperature outside and the sarking temperature at night, it's 7.3 degrees below the ambient temperature outside. So it's only 0.3 degrees warmer than the actual tiles themselves. So there's potential for condensation actually forming under the sarking as well, under the foil sarking. So common poor practice in Australia would be to build a tiled roof without any sarking at all. So this means we know when tilers get up on the roof during install or during maintenance, tiles can get dislodged or cracked. If you get high wind and rain events occurring, then wind can be driven through the overlaps in the tiles and may leak. The one benefit that this roof does have is that it has huge drying capacity. Because there's so much air leakage through those tiles, you're going to have huge air change rates in that roof. So that means it will dry out quickly. But then in 2001, CSRO made a statement again in a report they did for the Forest Wood Products Association. They said lack of sarking can result in excessive humidity cycling in roofs and result in excessive structural weakening of nail plates. So when you get the swelling and contraction of timber over time with the humidity, then you can get gradual pull out of those nail plates and structural weakening. So if we then look at a sark tiled roof, It's a preferred option because now we've got that sarking, which was obviously there to drain the liquid water. However, as I mentioned, that sarking still can become very cold, and there's a potential for condensation to form under that sarking. So when we've got higher humidity, warmer temperatures inside the house, and we've got vapor permeable plasterboard on the ceiling, vapor permeable insulation, then that humidity can potentially migrate up into the roof space. A large culprit for migration of humidity from the living space to the roof space is ventilated downlights. They'll allow all the heat and all the moisture from inside the house to go straight up into your roof space, increasing the potential for condensation in any roof system. A preferred option would be to use, in cooler climates, in particular in climate zone 4, 6, 7 and 8, would be to use a vapor permeable sarking under the tiles. So what this means is that the water vapour that might migrate up into the roof space can carry on, migrate through the vapour permeable sarking up into the cavity between the sarking and the roof tiles. If it does condense on the roof tiles, it can drop back down onto the sarking and safely drain away to the gutter. And then you've got that ventilation path between the sarking and the roof tiles to drive off any residual moisture. So my wife is actually German, and every year we go back to Germany to visit the in-laws. And my German's not so fantastic, so rather than speak to my in-laws, I go out and I take photos of roofs instead. And this is actually a roof that, of a house they built about 4 years ago. And I'll just take you through the construction method here, which is obviously tiles to deflect the rain. Then you've got a vapour pressure, which is pushing outwards. So all the vapour, high temperature, high humidity inside the house wants to push outwards to the colder conditions outside the building. And the way they construct this system is they use a series of vapour permeable materials to make up the roof structure, which is vapour permeable mineral wool, vapour permeable OSB, which is oriented strand board, and then vapour permeable sarking. And what this means is that if the vapour transports up into the cavity, condenses on the roof tiles, it will drop down, drain to the gutter, and then you have a ventilation path which is created between the vertical battens and the horizontal battens. So you've got the two batten approach, and the air moving up underneath will drive off any residual moisture. So in Australia, common poor practice, not recommended, is to use a metal sheet roof with no treatment under the metal cladding. This is probably, well, highly likely to form condensation and drip back down onto the insulation and ceiling linings. Common practice in Australia when sarking is used is to put it over the battens. This is still not a fantastic approach, because what's going to happen here is you've got the membrane in direct contact with the roof sheeting. So at night, when you've got the night sky cooling, the membrane is going to become exactly the same temperature as the sheet roofing. So if you're going to get condensation under the sheet roofing, you're going to get condensation under the sarking as well. A better approach, still not fantastic, but better would be to put the sarking underneath the battens. That means you've separated the cladding from the sarking. This is something we recommend more in the temperate climates. Probably still in the cooler climates, it's still not enough to maintain enough thermal gap between the sarking and the roof cladding to limit condensation. So a vapour permeable approach, using a vapour permeable sarking like the tiles, is a far better approach, as any moisture will be allowed to migrate up into the cavity where it can condense and drain away, and then the ventilation can drive off the residual moisture. So a typical approach for a foil face blanket is to put the metal sheet cladding to compress the foil face blanket over the battens. This is something that's commonly done in the temperate climates of Australia, and it's still perfectly valid for those temperate climates. However, when we go to the cooler parts, we say, well, if we have compression of that insulation over the battens, then if that's not enough thermal break to maintain the foil facing at a high enough temperature to prevent condensation, then we could end up with localised condensation around the battens. Additionally, if you have higher temperatures, higher humidity on the inside of the building with extremely cold claddings, then that means you've got a very large vapour pressure pushing the water vapour out. And when it pushes up against the vapour barrier on the underside of that foil face blanket, We know that it's very hard in practice to get a perfect vapor barrier. For the overlaps, potential damage to the membrane during install, all these things could potentially allow water vapor to get into the blanket. So over time, potentially accumulation of moisture. We are investigating approaches to start to enhance this system, which would incorporate a spacer over the top. So in this case, what you're seeing is a secondary batten over the top of that, which would then increase the thermal resistance between that membrane and the roof cladding at the batten point. Therefore, would likely to eliminate the risk of localized condensation at the batten point. And further to that, if we put a vapor permeable membrane over the top of that system, then any vapor that might want to migrate up or force its way up can carry on up to the metal sheet roofing, where it's allowed to condense on the metal sheet roofing, drip back down onto the vapor permeable membrane. Because we have those corrugations in the metal sheet roofing, it will drain down to the gutter, and the corrugations also provide air channels up to drive off any residual moisture in that system. So now what we've done is we've built in deflection, drainage and drying into that system using durable materials that will last a very long time. So if we look again at the German system, we say, well, how do we Australianise this? Well, obviously, we put metal sheet roofing on it. And what that does is it acts as a drainage for rain, and we have that vapour pressure, which is driving outwards, and it allows the vapour to permeate straight up. If it wants to condense on the sheet metal, it can condense, drip back down onto the drainage plane, drain to the gutter, and then we have that drying path up underneath the battens. So what this system actually looks like, it will look like something like this, where we have the option of putting insulation on the ceiling lining as well as at the roof line. We would have a rigid sheathing which would act as a support for the membrane itself, so it would be able to withstand higher wind loads. It has a drainage plane that's flat and uniform to drain off the water, and then it has that drying ventilation path built into it. For commercial roofs, generally speaking, in the cooler climates, we have a vapour pressure that goes outwards. So we've got that night sky cooling occurring, and we've got very cold cladding. We've got higher humidities and temperatures on the inside of the building trying to force vapour upwards. So we've got the metal sheet roofing to deflect off water or condensate that forms on the top of the sheet roofing. We have that foil vapour barrier on the underside of the mineral fibre, which is designed to stop or prevent the water vapour from pushing upwards into the blanket. If we then do have extreme conditions, extreme humidity or extreme cold on the outside, then if water vapour does push up into that blanket, we can add a vapour permeable wrap over the top of that system. So very much like the residential system, in that the water vapour can carry on up, condense under the metal sheet roofing and drain off through the profile in the metal sheet roofing. And we have those corrugations built into the metal sheet roofing, which allows for residual moisture to be driven away. So what we need to remember to design buildings or structures so that they're durable and will last a long time, we need to remember, or as a priority, we need to stop moisture getting in. So this is what the NCC and the new provisions for the weatherproofing are all about. It's about reducing the amount of water that will actually get into those construction systems. And then we need to allow moisture to escape should it get in. So we need to be able to describe to our friends, our colleagues, how we've actually built in drying paths into that system. If you can't describe how that system's going to dry, then maybe it won't. Then we've got the New Zealand learnings and what they learned from their expensive mistake in the leaky building crisis. They came up with their philosophy of the 4 Ds: deflection, drainage, drying and durability. So we need to deflect and drain the moisture, the water and the condensate. We need to build in drying paths, whether that be ventilation paths or vapour permeance into those construction systems, or a combination of both. And we need to select durable materials that will be able to withstand the amount of moisture which they'll be subject to. So what does the builder get out of this? They'll get reduced callbacks. They'll eliminate those ghost leaks, those leaks which aren't actually leaks, but they're condensate forming on the structure, dripping down onto the ceiling, which looks like leaks but isn't actually leaks. Reduce the mould complaints, reduce their liability. therefore improve the air quality of the buildings which they're offering, therefore reduce the asthma risk of their consumers, be able to market a healthy home to the purchasers of their homes. And that's it for me.